Hi, I'm Hamilton, doing it the Kiwi way. NAND equals not AND. If all inputs, are 1, then answer equals 0, else answer equals 1. Let's do the truth table for that. We use truth table. We've got inputs A, B, and the output Q. Zero, zero, 0, 1, 1, 0, 1, 1. If all inputs are 1, then the answer is 0. Otherwise, it's 1. And that's the truth table. And Q is equal to A and B, all knotted. We've got a new symbol here. The dot is equal to AND. This is also, you can also write Q is equal to A and B, all knotted. So when we omit the dot sign, it's assumed that we're using the word AND. Now let's draw the cMOS representation of this gate first. We're using transistors. We've got a VDD here, we've got a resistor, and then an AND is represented in series. We've got our inputs A, and an input B, and the answer comes out Q. So when we do an AND, the A and the B are connected up in series, one after the other. For this, that shouldn't be cMOS. That should be nMOS. For cMOS, what we do is we're going to replace this resistor here with a pull-up representation. And we'll just draw it here. This is pull-up network. And here we have a pull-down. And if you like, you can call that one A and B. So we've got a pull-down network. So when A and B are both 1 or high, then F, or in our case Q, is going to be 0. Otherwise it's 1, and this is the rule. Let's do our cMOS. For cMOS, remember that we replace the resistor with a pull-up network. And we'll do the pull-up network now. For pMOS implementation of the pull-up network, it's the complement of not A and B, and the complement is A or B. And for the pull-down network, we've got A and B, and notice how we omitted the sign, the not sign there. So now we've got this plus sign here, and in digital logic, plus is equal to OR. So let's do our VDD, and this is the cMOS. So we A or B for ORs, they're in parallel. We've got our B here, we've got our A here, and that's that one done. Now for the pull down network, A and B is like this here. Running out a bit of room, so I'll make it a bit smaller. And we've got A and B here. and our answer pops out Q here. This is a cMOS representation, and just a quick note or reminder again, we use cMOS to reduce the amount of power used by our circuit. We'll also reduce the size because we're replacing this resistor with something that's substantially smaller, which is a pull-up network. And also we get rid of the voltage divider rule problem, which is basically sometimes our answer may not come out as a true 1 or a true 0. Now the NOR. NOR equals not or. If one or more inputs are 1, then the answer is 0, else the answer equals 1. So Q is equal to A or B all knotted. Remember that plus is equal to or, and if we use it, dot is equal to and. Let's do the truth table for this one. We've got inputs A, B, and the output Q. Zero, 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 1, 1, 0, and 1, 1. If one or more of the inputs are 1, then the answer is 0, so that's 0 there, 0 there, 0 there, else the answer is equal to 1, and we've got a 1 there. Let's do the nMOS representation, transistor-wise. We've got our VDD up here, we've got our resistor, and then ORs are in parallel. Ground, and the answer Q pops out here. So it's good to draw this again, the digital logic. A and B here, and Q comes out here. So when they're both 1s, we get the answer 0 here. When there's a 0 or 1, we get a 0. When they're both 0s, we get a 1. We can also describe this. This is an OR gate. This is a NOT gate or an inverter. You can see it from the inversion of the symbol here. And this little circle right here is also saying not it. Now we've done the nMOS representation, and as we know, we'll replace this resistor with a pull-up network. And this here is the pull-up network. And here we have our pull-down network. Hopefully becoming a bit more familiar now. And we've got our transistors up here. T1 and T2, part of the pull-up network. And T3 and T4 is pull-down network. Now we're going to draw the cMOS of it. So we replace the resistor. Just check and see what I've done. So Q is equal to A or B all knotted. So the pull up network is A and B. And the Q pull down network is A or B. And notice how we've omitted the not sign here. The cMOS, we'll do our VDD. We replace the resistor with the A and B. ANDs are in series, A and B. And we've got an answer Q coming out here. Now we do our pull down network, which is the nMOS implementation of it, which is in parallel. A, B, and that all goes off to ground. Remember that these pMOSs are about 2.5 times bigger than the nMOSs here, but that is basically, say, 5 in size, whereas a resistor would be about 1,000 in size. And then we've got our sizes down here, which is a 1 and a 1. So we substantially reduce the size of our network and at the same time reduce the power consumption and got rid of the voltage divider rule problem. And here is a diagram I put up, and we'll practice drawing that again. Means knotted. Got an A and a B and a Q coming out here, and there's our truth table as well. I think that covers that one off.